So this presentation is about refactoring scientific software. So we start out by defining what is refactoring, and the sentence in red basically gives the formal definition of refactoring, that it is a disciplined technique for restructuring an existing body of code, altering its internal structure without changing its external behavior. So the important things to notice about this is that this is not the same as development, where you may be starting from scratch and slowly building up a working code. What you're starting from is a working code. You know and you understand the behavior of this code. And the most important thing is that you have a baseline that you can use for comparison purposes. The reason why you may want to refactor could be many. The most typical ones that one encounters is that you want to clean up the code and to improve its sustainability. So you basically want to make it more modular. Maybe you want to release it to the outside users. So far, it has been just used by your own internal users, and now you want it to become more easy to understand and use so that other people outside of your close group of collaborators can use it. It may happen in order to move to new platforms where the constraints of performance may require different way of data layout or even different algorithms sometimes. And the final one is that you may want to expand the capabilities of the code, and so what you need for that is structural flexibility. So go back to our running example. This was the one that I mentioned in the design. So if you go to the repository that we have pointed you to, there are two versions of the code. One is a single file with the monolithic code, and the other is a modularized, reusable, and maintainable code. If we were given the first code, which is a single file with monolithic code, then we would be exercising then the refactoring would be resulting in the kind of code that is the second version of the code if we got the refactoring right. So, but before we launch into that, we have to think about why we refactor. So it's important to know exactly why you are refactoring. Is it really necessary? And also to have a very clear idea of where you want your code to be after you're finished with the process of refactoring. So in the heat example, it is necessary because it's a monolithic code. There is no reusability in any part of the code. So devising tests for this is difficult because anytime you run, the whole code runs. So there's no question of being able to do any sort of unit testing. And you have very limited extensibility. So where do we want to be after refactoring? We want to be closer to the second version, which is more modular, maintainable, and extensible. So that answers the questions that we had about why we were refactoring and where we wanted to go with refactoring. Then the other considerations that one has for refactoring is one should always know before you embark upon the process, you should know what should be the scope of your refactoring. So how deep a change and how much of the code is going to be affected. So again, we go back to looking at the heat example. The reason why we were refactoring is there was no capability. So what is the scope? We are not doing any capability extension. We do not have any performance consideration. We just want a cleaner and more maintainable code. So those are our objectives in that particular example of refactoring. So to convert the monolithic code, what we do is we separate out utilities, we generalize interfaces, we put some global definitions in a header file, and we create a general build function. So what we are doing is no new code or intrusive changes within the capabilities, that is the actual numerical part of the code. We are just restructuring it and reorganizing it. So there are no intrusive changes involved in here. Third consideration, before starting, you should know your cost estimates. You should have a method for verification. With the first step in that is check for coverage provided by existing tests. If you don't have a good coverage with the existing tests, then you should develop new tests where there are gaps. And you should also make sure that the tests exist at different granularities, which means that it not just the unit test, but also there should be very demanding integration and system level tests. There is a reason why the word demanding sits in there. It's because you can devise a test uh, for exercising a capability, and it may pass. If it doesn't, for example, if you have a numerical method that is not very sensitive to perturbations, or it starts to go into regimes. I don't understand why these things automatically turn up. Anyway, um, it should be that such things, changes in behavior should be captured immediately and quickly and should be pinpointable. The next thing that we want is we want to know your bounds, in the sense that you should know what is acceptable behavior change. Uh, for example, because in scientific codes we work with floating point numbers, bitwise reproduction is going to be extremely unlikely if you change the order of calculations in any way. So you should know the acceptable error bounds ahead of time in order to be able to track changes as you're refactoring your code. In your head, you should have a clear map from here to there, in the sense that you should know what you want your codes to look like when you're finished with the refactoring process. And when you are doing your cost estimate, basically make sure that you incorporate testing overheads into the refactoring cost estimates. If you have to develop new tests, they should be part and parcel of the cost estimate, because they are um, that's non-negotiable. You should have enough tests. Okay, so we go back to the running example and do the refactoring of the running example. So we want to convert heatall.c in the repository to a cleaner version with the reusable code. You can do this if on your own, and as David mentioned before, that we are very happy to accept your pull requests with your exercises that you may want to do yourself, and we can give you feedback after you've done your exercise. So, oh, I'm sorry, that one you're doing it yourself, but the example that I'm walking you through is the second example, where I'm taking a clean solution and generalizing it to update solution interface. So right now what we have is, we have three different, if we go back to the design, to that repository, you will see that we have three different implementations of heat.c, one for each uh, method of integration that we are utilizing. So for this exercise, we will use FTCS and Upwind 15 as alternative options, and we will generalize it into a single heat.c, and then add, so that we can add another method without modifying the code. So here we are preparing for refactoring. The first thing we do is we run code coverage. We check for coverage. So we run heat with runtime of ftcs.result, and we get the gcov of heat.c and examine it. When you're looking at the coverage, what a dash there indicates that it is a non-executable line. So as you see, wherever there are curly brackets, it's a non-executable line. A number indicates the number of times that the line was called, and a series of hashes indicates that the line wasn't exercised at all. So here, what this snapshot is showing you is that the upwind 15, crank n, etc., were not exercised, and therefore we need to provide another baseline in order to have code coverage. So we run this whole thing again. Now we run the heating algorithm as upwind 15 and generate our runs in another directory called upwind results. And when we run coverage now, we can see that even though that now we don't have coverage for update solution FTCS, we have coverage for update solution upwind. So we have baselines for FTCS and for upwind. So we are ready to do the refactoring, where we combine these two into a single heat.c. So our starting code looks like this. We have update solution FTCS, update solution upwind, and update solution crank Nicholson. We turn them into external booleans. And also we noticed that the initialization for Crank-Nicholson is different. So the interfaces are not identical. Crank-Nicholson has an extra argument, and it also has an extra step in initialization. So the way we do is for our generalization, we generalize the interface. So we turn it into an update solution, and we add an extra uh, uh, argument here that tells which particular version is it that we are going to use. We modify the make file where for different versions now we can have a separate collection of sources, and that produces different executables, and we then add null implementation for initialize crank because we don't want it to be used in FTCS and Upwind 15. And so you will know, so and then what we have is we modify the implementation here. The update solution now looks somewhat different from it did in the previous case. Now what we do is we make heat 1 and we generate the FTCS results, make heat 2 and run the upwind results and verify against baseline. So what we had in the previous instances was that we could build just once, but at the runtime, we had to give arguments in order to get the integration method we wanted to use for evaluating the results, but they needed to change every time we were using, so we needed to write new code and make changes to the code if we wanted to add a new integration method. Now what we have is we've changed the need for change the need to rebuilding, but the code itself doesn't need to change, and we can keep on adding as many new methods as we like without having to change the code itself. So this was a toy problem. Now we go to a much more complex real life example from Flash. Here we are refactoring from the for the next generation hardware. So what we are doing is we are changing our supported AMR package from Paramesh, which is not supported anymore, to AMRX, which is being made ready for exascale. So our plan includes figuring out how do we get from here to there, what is our on-ramping plan, the design that we need to take into consideration, the intermediate steps, and finally realizing the goal. So this is what the ultimate transition looks like, and I'll go over each stage one by one to give you a feel for things that we changed. So the cost estimation included expected developer time, extent of disruption in production schedule. And so because of that, we got a buy-in from the stakeholders that included the users for development and disruption times. Our initial estimate was 6 to 12 months. It actually took closer to 12 months. Now I'll walk you through the stages of the refactoring process. So we started out with Flash version 4.4. For MRX mesh, we did the requirements gathering for how we needed to change the interfaces in order to accommodate MRX mesh. And we picked up the simplest version of hydrodynamics we had, basically removing most of its functionalities and its complexities, and created a very simple version again that we could exercise over and over again and run very quickly in order to exercise the AMRX interfaces. So what we did was we modified the grid API and introduced iterators on top of simple hydro, so that simple hydro wouldn't know whether the iterators are getting it state data from an AMRX implementation or from a Paramesh implementation. And so we introduced Grid API as a new, under the Grid API, we introduced a new alternative implementation. At this point, we were supporting both Paramesh and AMRX. And because AMRX provided the blocks to Hydro to work, to the data to Hydro to work on through iterators, we built iterators over Paramesh as well. The next thing, so here we were still in this stage, we were still exercising both Paramesh and Grid and AMRX in strictly uniform grid mode just to make sure that the APIs are working fine. In the next stage, then, we started to exercise the AMR capabilities, which includes things like flux correction and top level interaction. We changed the hydro driver for a real hydrodynamics code, which would do the iterators, which would be using the iterators in order to do the calculation. So now we had a full new new grid unit implementation, and we had a whole bunch of code that was coming from old Flash. But now our hydrodynamics could work interchange with full features with interchangeably with AMRX and Paramesh. So these were the steps in the process that we took. And so from looking at the toy problem as well as this more general example, these are the takeaways from this presentation is to have a good outcome from refactoring, you should know why, you should know how much, you should know the cost, you should plan including the ramp up. All through the process, you should have strong testing and verification, and you should get a buy-in from stakeholders. So that brings me to the end of this presentation.